To determine the minimum size THHN conductor for heating, ventilation, and air conditioning unit with the specified parameters, we need to refer to the National Electrical Code, specifically Article 310.16. The heating, ventilation, and air conditioning unit has a minimum circuit ampacity of 62 amps, a maximum overcurrent device rating of 70 amps, and operates at 480 volts, 3-phase. According to Article 310.16, which provides ampacity ratings for conductors, we need to select a conductor size that can safely carry at least 62 amps, considering the allowable ampacity for THHN insulation. THHN insulation is a thermoplastic high heat resistant nylon coated wire. It is commonly used in electrical wiring because of its heat resistance, moisture resistance, and abrasion resistance. THHN conductors are suitable for dry and damp locations and have a temperature rating of 90 degrees Celsius. Based on the NEC Table 310.16, a number 6 American wire gauge copper conductor with THHN insulation has an ampacity of 55 amps at 75 degrees Celsius, but a number 4 American wire gauge copper conductor with THHN insulation has an ampacity of 70 amps at 75 degrees Celsius. A number 3 American wire gauge copper conductor has an ampacity of 75 amps at 75 degrees Celsius, and a number 2 American wire gauge copper conductor has an ampacity of 95 amps at 75 degrees Celsius. Because the minimum circuit ampacity is 62 amps, a number 6 American wire gauge conductor is not sufficient. The 70 amp rated number 4 American wire gauge is also not sufficient because the next size up roll in 240.4 p would not apply since the overcurrent protection is not greater than 800 amps. So you need to feed the 62 amps with a conductor rated 62 amps or greater. With all of this being said, we need to use a number 2 American wire gauge conductor because it has an ampacity of 95 amps at 75 degrees Celsius, which is more than 62 amps. Article 240.4. D addresses conductor protection, stating that conductors must be protected against overcurrent in accordance with their ampacities as specified in 310.15, unless otherwise permitted or required in 240.4. E through G, the overcurrent protection device should be sized to protect the conductor in accordance with its ampacity. In this case, the maximum overcurrent device is specified as 70 amps. The number 2 American wire gauge conductor is more than sufficient, as it can handle more than 70 amps. However, the 70 amp overcurrent device would be acceptable. In addition to conductor ampacity, voltage drop must be considered, especially over long distances. Voltage drop occurs due to the impedance of the conductors, and excessive voltage drop can cause equipment malfunction or premature failure. The recommended voltage drop for feeders is typically limited to 3%. The formula for voltage drop in a 3-phase circuit is voltage drop equals the square root of 3 multiplied by the current, multiplied by the length of the conductor in feet, multiplied by the impedance of the conductor per foot, divided by 1000. To calculate voltage drop, you need to know the conductor impedance, which can be found in the NEC Chapter 9, Table 9. The impedance values are given in ohms per 1000 feet. For a number 2 American wire gauge copper conductor, the impedance is approximately 0.194 ohms per 1000 feet. Given a distance of 285 feet, the voltage drop can be calculated as follows: voltage drop equals the square root of 3 multiplied by 62 amps multiplied by 285 feet multiplied by 0.194 ohms divided by 1000. This results in a voltage drop of approximately 5.53 volts. The percentage voltage drop is calculated as voltage drop divided by the source voltage multiplied by 100. So, 5.53 volts divided by 480 volts multiplied by 100, which equals approximately 1.15%. Since 1.15% is less than 3%, the voltage drop is within the acceptable limit. Therefore, a number 2 American wire gauge THHN conductor is suitable for this application, considering both ampacity and voltage drop. Concerning the feeder classification, according to Article 100 of the NEC, a feeder is defined as all circuit conductors between the service equipment, the source of a separately derived system or other power supply source, and the final branch circuit overcurrent device. In this scenario, the circuit runs from a 70 amp breaker in the panel to a fuse disconnect mounted on the heating, ventilation, and air conditioning unit, which serves as the final overcurrent protection device. This meets the definition of a feeder. It is a circuit that supplies power to utilization equipment, in this case the heating, ventilation, and air conditioning unit, and it is the final overcurrent device in the circuit, the 70 amp circuit breaker in the panel. Therefore, the circuit is indeed classified as a feeder. In summary, the minimum size THHN conductor for the heating, ventilation, and air conditioning unit is a number 2 American wire gauge, and the circuit is classified as a feeder according to the NEC. Always consult the latest edition of the NEC and local electrical codes for specific requirements and regulations in your area. Also, ensure that all electrical work is performed by qualified and licensed electricians to ensure safety and compliance with applicable codes. The selection of conductors and overcurrent protection devices is critical for ensuring the safe and reliable operation of electrical equipment. Incorrectly sized conductors or overcurrent devices can lead to overheating, equipment failure, and even fire hazards. Therefore, it is essential to follow the NEC guidelines and best practices for electrical installations. Firstly, always verify the minimum circuit ampacity and maximum overcurrent protection device rating for the equipment being served. This information is typically found on the equipment nameplate or in the manufacturer's specifications. Secondly, select a conductor size that has an ampacity rating equal to or greater than the minimum circuit ampacity, taking into account any derating factors for ambient temperature or conduit fill. Thirdly, choose an overcurrent protection device with a rating that does not exceed the maximum overcurrent protection device rating specified for the equipment. Fourthly, calculate the voltage drop for the circuit to ensure that it is within acceptable limits. If the voltage drop is excessive, consider increasing the conductor size or using conductors with lower impedance. Fifthly, ensure that all conductors are properly installed and terminated in accordance with NEC requirements. Use appropriate connectors and torque specifications to prevent loose connections, which can lead to overheating and equipment failure. Finally, always perform a thorough inspection and testing of the electrical installation to verify that it meets all applicable codes and standards. Use calibrated test equipment to measure voltage, current, and insulation resistance to identify any potential problems. Remember that electrical work can be dangerous, and it is always best to err on the side of caution. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. By following these guidelines and best practices, you can ensure the safe and reliable operation of electrical equipment and protect yourself and others from electrical hazards. Additional notes to consider include the maximum overcurrent device rating, which is 70 amps, is within the allowable range of 125% of the circuit amps, which is 62 amps. 125% of 62 amps is 77.5 amps. The 70 amp overcurrent protection device is less than 77.5 amps. Secondly, the distance of 285 feet does not exceed the maximum allowable distance for a number 2 American wire gauge THHN conductor at 480 volts. The conductor is adequately sized for this application and the length of the run. In addition to copper conductors, aluminum conductors are also commonly used in electrical wiring. Aluminum conductors are lighter and less expensive than copper conductors, but they have a lower ampacity rating and higher impedance. When using aluminum conductors, it is important to select a larger size to achieve the same ampacity and voltage drop performance as copper conductors. The NEC provides ampacity tables and correction factors for aluminum conductors, which should be consulted when sizing aluminum conductors. Another important consideration is the type of raceway or cable assembly used to enclose the conductors. The type of raceway or cable assembly can affect the ampacity of the conductors due to differences in heat dissipation. For example, conductors installed in a tightly packed conduit may have a lower ampacity than conductors installed in free air. The NEC provides dirting factors for conductors installed in various types of raceways and cable assemblies, which should be applied when sizing conductors. Grounding and bonding are also critical aspects of electrical installations. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock hazards. Bonding ensures that all metal parts of the electrical system are electrically connected, which helps to minimize voltage differences and prevent shock hazards. The NEC provides detailed requirements for grounding and bonding, which should be followed carefully. Surge protection is another important consideration, especially for sensitive electronic equipment. Surges can damage or destroy electronic equipment, and surge protection devices can help to mitigate the risk of surge damage. Surge protection devices should be installed at the service entrance and at individual equipment locations. The NEC provides requirements for surge protection devices, which should be followed when selecting and installing surge protection devices. Arc fault circuit interrupters are also becoming increasingly common in electrical installations. Arc fault circuit interrupters are designed to detect arc faults, which are a common cause of electrical fires. Arc fault circuit interrupters can help to prevent electrical fires by interrupting the circuit when an arc fault is detected. The NEC requires arc fault circuit interrupters in certain locations, such as bedrooms and living areas. Finally, it is important to stay up to date on the latest changes to the NEC. The NEC is revised every 3 years, and it is important to be aware of any changes that may affect your electrical installations. The NEC is available from the National Fire Protection Association, and it is also available online. By staying informed and following the NEC guidelines, you can ensure the safety and reliability of your electrical installations.